All right, good afternoon again from Sven Kuhi, multi-product team leader. Today's quick webinar is talking about SolidWorks Flow simulation, and the specific topic is about optimized cooling strategy for electronic components using flow simulation. The first thing I would like to review is the agenda today. The first concept is why we need simulation. And after that, we're starting with the case study in order to understand the optimized cooling strategy for an electronic component using flow simulation electronic cooling module. We will have an electronic electronic enclosure, as you can see in the picture, with a variety of configuration. Right now, you can see the internal fan and specific heatsink here. The second configuration you might, let's say, start thinking is about external fans, and the same, let's say, heatsink. And the last configuration is again into external fan, and we're talking about pin heatsink. So we will understand how we set up those studies, how we can modify the design, and later on we compare the results. And at the end, what is very important to understand is to find out more figures and exact figures about return of investment. So if you get SolidWorks Flow simulation into your profile, how much return of investment you might have in the future. All right, so with that introduction, let's start with the first one, why we need simulation. In a traditional procedure, all the designs are happening in a 3D CAD model. We're building the physical prototype, and then we move to test performance in a real model. What is happening if there is any error or problem detected in test performance stage? We have to get back all of these stage again from the design, rebuild the prototype, and again come to the test. These procedures involve a lot of series effort and let's say a variety of people to incorporate, and that could be very time consuming and more importantly can be very costly. But instead, if we can suggest for a designer and engineer to have the option of doing the 3D CAD design, then having a virtual prototype on the same time, and at the same time we do simulate the performance, or let's say we have a virtual testing facility here. What is happening? Any problem, any errors we detect within the same time, we can get back to the design without having the actual physical model built. We can go back, change it, and retest. And we can, let's say, repeat this procedure until we get a validated model. And then we can go for the final product manufacturing. So if you look at the typical serial procedure in a traditional procedure, all the design concepts are coming to electrical design or mechanical design. Then after that, we do the design validation and technical communication, and then we go for operation. But with SolidWorks proposal, all the design stage, design validation stage, and technical communication, and also on top, product data management are happening parallel. And this is exactly where we're saving time and money. So for that very obvious reason of cost, time, and resources, if we can have a tool or facility to shortcut and make the serial process converted to a parallel process, we are the winner. So that's why we need the simulation. Now let's have a closer look about the solution we have with SolidWorks Flow Simulation. You can see the base software of Flow Simulation can do a variety of, let's say, applications such as internal, external flow, heat transfer study, having rotating components like fans, blades, turbines, and etc. compressible and incompressible flow, Newtonian, non-Newtonian flow, laminar and turbulent, and also time dependency. And a very important feature we have here is the result exchange. Means when you're finding the flow field result, such as pressure, you can export it to any structural analysis in FEA within SolidWorks and understand, for example, the stress or deflection on the structure. On the next level, which is an upgrade or an add-in to your flow simulation, we have specific, facilities for electronic cooling module. And one of the very important one is extended database, and this is what we are going to review today. Joule heating is supported, PCB generator is there, and also we have the facilities for heat pipes. These could be separated from the last add-in you can see, HVAC. Well, anybody in this category of design, they can understand the comfort parameter. Again, the database, engineering database is specialized for HVAC, application. Tracer studies and advanced radiation is something you can have here. Just letting you know, flow simulation is the base package, which definitely getting added to your CAD. So it's not coming as a standalone product. You need SolidWorks CAD first. Then you have flow simulation on top. Then if you like to activate either electronic cooling module or HVAC, there would be an upgrade. Noted, any of these can be separated and can be added separately. Now today what we are going to understand and experience within our case study is the case of internal fluid with a heat transfer application active and specifically using electronic cooling module. All right, now let's have a look through our case study. As you can see, we have a main design here as electronic component, hips of heat sinks and electronic parts with perforated plates and etc. We are thinking to have the best design selected within 3 different idea or concepts we have. If we have internal fan, external fan, and changing also the heatsink type. On top, we have to understand the boundary condition or working condition. So for the first, set of problem, we have PAPSAT fan, the real off-shelf fan, and we are going to experience how we can select it from our extended database. We have all the perforated region fully removed for simplicity of the analysis and replace them by dummy leads, and they are exposed to environmental pressure. As you can see, we have a heatsink, and simply under that we have a main chip and 2 resistor component with the power generation of 15 watts. We have PCB circuit PCBs with electronic box for 4-layer PCB configuration. And also we have some heat generation in other components. What is very important for us to understand the performance of the fan, what is the fan average flow rate, what is the main chip maximum temperature, what are the transistors maximum temperature, and also RAM chip maximum temperature. So for that specific goal, we are going to set up some parameters. Alrighty, let's move on to the case study. As we said, guys, if we're looking at my design and looking at the configuration, the original model, as you can see here, we have the electronic box and it got variety of section, variety of components. As you can see in the list, we have assemblies and sub-assemblies. And then you can see perforated plates on the sides and on the top and bottom we do have. So the main idea, we have very tiny passages through these perforated plates. And if we can simply eliminate them and replace them with dummy components or virtual perforated plates, we're saving a huge time to get our analysis done. For that reason, we introduce a couple of simplicities. First, the internal fan configuration. You can see all the perforated plates being suppressed. And then we suppress the internal fan and instead we put the sides for external fans with the heatsink configuration, as you can see. And next, same fan system, but I have a pin heatsink. All right. Now, what I would like to do is to first start with the internal fan analysis. In order to create any flow simulation, what you can do, simply you can start with the wizard, give it a name to your project, and select any configuration or create a new configuration into your design. The next question we have to answer is what sort of unit system we use, which all of them can be modified to the point of interest. For example, temperature to centigrade. Next, the type of analysis, internal or external, if any conduction active, if there is any radiation active. If you would like to look at the result over the time from 0 second and see what's happening after 10 minutes or 1 hour, if gravitational effect is active, if we have any physical rotating components. So you have the fan blades and you don't want to replace it with a virtual fan. And the main idea is to understand how much torque is required, or in the case of a reverse application, how much torque is generated. All right. Next, you have to choose your working fluid. For example, you can see we have air. You can see all the categories, and this is one part of our, let's say, engineering database, as you can see here. Next, you have to choose your main solid material. Look at the interaction of internal case with the outer space. Either you have adiabatic walls around your internal case, or you would like to put even heat transfer coefficient around it and see what is happening. And the last question we have to answer, what are the initial conditions in terms of pressure, temperature on fluid, solid, and any existing velocity in the field. By clicking finish, you will create your SolidWorks Flow simulation, and all we said can be easily reviewed by looking at general setting, and you can see what is being created. All right. You can see when you create a flow simulation project, you have two main sections, input data and result section. So you can complete the, let's say, problem definition by going into your input data and add a variety of components as you like it. For instance, we said solid material is dominantly, for example, aluminium, but if you look, different components got different material on it. That's where you go to solid material, insert a solid material, and then you select it from the database. And this is one of the very interesting part we have. You can see, for example, in the category of predefined, we have a variety of subcategories such as alloys, building material, and etc. In order to access the database, you can access it here. And this is the real asset for SolidWorks Flow simulation. You can see there are heaps of, let's say, different information we are storing here in regards to, let's say, information about cities, contact electrical resistance, thermal resistance, fans, heat sinks, materials, perforated plates, printed circuit boards, porous media, and you can see the huge list. And under each category, there are subcategories, and then you can obviously go and have a look, select any, look at item properties, and also all these item properties could be table dependent as well. So it depends on what we select, we can make any choice. So if by any chance what you're trying to add to your SolidWorks Flow simulation is not listed there, you obviously can define it in user define or custom define, and simply going here, instead of predefine, go user define and create a new item. All right, so with that explanation, you can see I've put aluminum here, I've put ABS polymer, TSOP solid material for these resistors. For this contactor, I've got any other one, and again, I can go edit definition and you can see what I've really selected from this category of IC package. You can see there is a lot of different components stored here, and the item properties, which is saving you huge time to find the properties of each component. Big project with huge a variety of components, that is a significant time saving. All right, after this point, we need to set the flow condition, which is coming to the boundary condition. As we said, we had perforated plates, we removed them, we add some leads to it. What we have to tell the software, as these leads, either in and outs or top and bottom, are exposed to environmental pressure. Any boundary condition can be set as inlet or outlet, volume flow rate, mass flow rate, or velocity, or pressure condition, or even wall condition. From this point, we can go and add a virtual fan with the off-shelf, fully determined properties. So insert a fan, and you can see what I've done. I select the face that the fan is applying and went through the database. And again, this is a huge database we have. If I go to electronic cooling database, you can see fans predefined in a category of axial. We go PAPSAT, and these are all PAPSAT fans being entered. And interestingly, you can see the item properties. You can see the fan curves is simply being stored here, and you don't have to do anything. So these are real components in a real world off shelf. That is something we usually using every day. All right. So there are fans I've put, first, second, and third fans. After that point, I've specified my heat sources. You can see 8 watts heat generation rate on these resistors. 3 watts are here. 40 centigrade on the other component. 4 watts is generated here. 1 watt is here. And 60 centigrade on the other side. And again, applying any of these boundary condition is very easy. Insert surface, volume, or even data from a model, and simply predefine it. So if you remember, we said we simply eliminated the perforated plate and we put solid material, but in fact they are not solid. For that reason, we have a perforated option, and we can insert. For instance, for the front and back, if you see, I've selected all the faces of leads, and I said I need a perforated plate. This time it's user defined, and what I've defined, there are hole shape in round, diameter of 0.004 millimeter, and the coverage is free area ratio of 46%. So simple as that, you will have a very simplified problem with all the items of perforated plates being fully defined here. Now we take it from there, and the next thing we would like to say is what we have as a microchip here. And we said this is a 2 resistor component. Again, from the database, you can see there are heaps of information of predefined off-shelf components. And in item properties, you can see the junction case heat generation and the junction board heat generation. Okay, so with that one, we go ahead, select what we want, or if we would like to create some, we do. And the heat source is 15 watts, as you can see. The last thing I have to put as a boundary condition, as I said, we have printed circuit boards, and you can see again from our database or user defined, we have a PC board, 4 layers, item properties, and all the item properties being listed here. If any of them needs to be table dependent, they are all listed. Conducting layer, we have 4 layers with the layer thickness and percentage cover. So fully define what you have as a reality as a PCB board. Okay, that is simply going to finish what we have as a boundary condition. Before we go for the solution, we mentioned there are things that we would like to follow up as a result, and they're very important to be focused on. That's where we put in goals in a case of global, point goals, surface goals, volume goals, or even combining all of them as an equation goal. For instance, what is happening through the fan is very important for me. So I've made the face where the fan been inserted, and I'm tracing the volume flow rate. Or I would like to go and see what is happening on this specific component as a maximum solid temperature. One of the chips I've got on the back. So any parameter at any specific place, either on surface, on the point, or on the whole volume, can be traced by goals. Now we are ready to solve the problem and show the result. Now, when you do the solution, you have a very interactive, let's say, screen. You can see the progress of the solution, convergence, and etc. When it is finished, you can go to the variety of plots. One of them, which is very popular, is cut plot. So in any cut plot, you can select any plane you have to show contours, isolines, vectors, streamlines, or mesh for a specific parameters such as temperature. So if I select both of them, I can view and see what is happening. I have to hide the model, and you can see this is what I have in this cut plot. Interestingly, you can play it, and there is no need to go over different plots to understand. In one animation, you can see what is happening from top to bottom of this enclosure. The other thing we can create as a plot is isosurfaces, means I would like to see the volume or the places which temperature is 32, and here it is. It can show me where and in which region I have those kind of temperature, and you can add more and more and have more and more isolation and see the critical area for yourself. Next type of plot is flow trajectories. What we would like to understand is the 3D format of the flow with the arrow type, and what I can do is simply show it to you, and this is how the flow in a 3D format is simply getting circulated. We can understand more about the circulation zone, the distribution, the temperature, also the velocity and everything in a vector format, and it's animative. You have a lot of other options to, let's say, add, for example, particles in the flow and see the erosion rates, and simply find out the best performance. Up to this point, we saw all the 3D, let's say, plots. There are more opportunities here. Either you would like to evaluate anything on the point, or let's say I would like to see on this surface list of the parameters. As you can see, what is the pressure outlet, what is the total pressure, what is the dynamic pressure, what are the velocity at the exit. You can see I've selected the faces and I've evaluated all these parameters here. So any parameters in terms of values can be, let's say, evaluated on points, surfaces, and volume. And obviously at the end, what I would like to say is all of the goals you have put, you can see it in a summary or in a history of how much is the final temperature of the solid as one of your goals you have been assigned here. So these are all your post-processing options. From this point, since we have different configuration, we easily can duplicate or colon the study and select any other configuration we have, and that is going to apply all of this boundary condition again and the top of the, let's say, plots you have prepared on a second configuration, and rerun the study. And at the end, you can see I have the option to right click and compare the result. Now you can see, interestingly, any of those plots I've created, which is common in all these three studies since I have coloned the projects, simply can be observed and compared. So for example, goal plot 1, for all these three studies, I can go for comparison. So it's going to extract the data for me of what is the values. or later on, if I like to have a chart or Excel file, let's say prepared out of this comparison, there is no problem. I can do that. So since this has been finalizing, let's say I would like to look at the summary, which is here, and then I would like to see the history, which is here. So over the iteration, over the values, average values, maximum, minimum values, and obviously export it to Excel file and see this one. All right, so what we see as a result at the end of this case study. Let's see. Among all of these results, what we can see, the last configuration, which is a pin fan, got the highest temperature on the CPU, and the best one is here is the fan. Then we have external fan, and we have the other format of the heatsink. This is what is showing us as a flow temperature, and this is exactly the temperature of the heatsink, which is directly going to our CPU. So with the option of compare, you can easily generate all those figures and graphs and simply do the comparison and find the optimized, let's say, cooling strategy for your design. Now, very quickly, it's the analysis about return of investment. And what I would like to show you here is the service I can definitely provide for anybody who is interested. You can see I do have an online calculator, which is simply telling us about the ROI. We selecting the company name and let's say business or industry. The main question we have to answer is how many people are working, how much is the salary, anticipated growth in a project for the next 2 years or starting from next 2 years. How many let's say design or development is happening over the 12 months, how much growth we are expecting, if there is any simulation in-house or it's outsourcing or no simulation. And also I've put a very low figure as there is no scrap at all here, and we are just a revenue of $1,000. These are not real figures for sure, but I would like to show you even a very low figure and see what are the benefits look like. So if we go to the benefits and what we can see, the annual saving over 3 days is $174,000, and the total saving is simply $5,000 to $3,000. As we said, there is no scrap, no reducing cost, but improve the efficiency, improve the effectiveness, and you can see the details here. And obviously, if you go to the last tab here, you can see I've put my, let's say, cost of investment as well here, as how much you put initially for SolidWorks Flow simulation, for instance, how much you're paying for subscription, how much you're paying for training, and how much internal management and support you are investing on. So these are what you are paying, and this would be the last and total cost. We can see a significant, let's say, saving of $84,000 even for the first year, $171,000 for the second year, and $267,000 for the third year. As I show in this figure to you, guys, after 5 months with whatever I put here, well, the real figures are much higher. We have scraps, we have, let's say, variety of team members, we have so many other more costs, but I've made all the costs as minimum. Within 5 months, we return the cost, and these are the net benefits and total investment values and return of investment. So it's a very huge figure. And I'm always saying the cost of the software in terms of cost of manufacturing, cost of testing or prototyping is not a fraction of seconds. All right, so with that one, I'm going to conclude this webinar. If you are interested for more technical or commercial information, or even if you like to have a case study with ROI analysis specifically for your, let's say, company, please let us know. We definitely help you to prepare your case study and start using our software and get proficient. We're providing range of training, a very big support team, and obviously a very robust integrated solution to do the job. Alrighty, guys. Hope you enjoyed the session. We have more sessions are coming from tomorrow again, and hopefully see you all on our next webinars.